Swayam Prabha. Digital India. Educated India.
Let us first review our earlier lecture, that is lecture 1 on torsion of non-circular shafts. We have noted few things, that while applying torsion, each section is going to have warping, and that warping is a solution of Laplace equation, and we have noted that the section is subjected to shear stresses, which will have a typical feature that shear stress cannot be acting normal to the boundary. If you have the section like this, what we have found that at a point in the boundary, the stress which is normal to the boundary, it acts in the radial direction. So, therefore, this tau zr stress is 0. So, tau zr is 0. So, therefore, all along the boundary you will find that stress is going to act only parallel to the boundary. This is a very important point. In the case of torsion of this type of component, shear stresses act parallel to the outer boundary. We have also introduced the Prandtl stress function, and this Prandtl stress function phi, it was defined that tau zx stress is given by the slope of the phi surface with respect to in the y direction. Similarly, tau zy is negative of the slope of the phi surface in the x direction at a point. So, this is something again important, that if you are trying to think of a section like this, suppose you are interested in finding out the shear stress at this point, it is going to be parallel to the boundary. So, therefore, there can be only shear stress tau zy, and if this shear stress is to be calculated, what we need to take? We take a section of the phi surface with a vertical plane containing x axis. Suppose I take that section of the phi surface with the plane containing x axis, this is the shape of the phi surface. So, we take a section passing through this line, and therefore, this is the phi surface, and therefore, if you now try to take the slope of this phi surface. So, this slope, let us say alpha, tan alpha that tan alpha will give us the stress tau zy, and you see that here the slope is negative and therefore the stress will be positive and it is really acting in the positive direction. Now think of it, if you are interested in finding out the stress at this point, and this stress could act only in the direction, if it is a positive stress it will be directed like this, so therefore it is going to be tau zx stress, here in tau zy will be 0. And now if we have to find out this, then what we need is that we have to take a section of the phi surface considering a vertical plane containing the y axis. So you have to take a vertical plane containing the y axis and then take this section. Suppose we take this section and draw it here, let us say that the phi surface intersection is like this, wherein I mean that we have the plotting of phi like this and y is here. Then at this point, if I take the slope here, slope of the phi surface, that slope of the phi surface, this angle alpha 2, tangent of that angle will be giving us the magnitude of the stress tau zx. And if this slope is negative, then obviously this minus minus will become plus, and therefore we are going to get the stress to be directed in the opposite direction. So therefore if I have this angle is negative minus tan alpha, then we are going to get stress to be again acting in the opposite direction. That means it will be acting in the direction like this. No, I am sorry, this tau zx is given by delta phi delta y. So if this angle is negative here, so therefore this stress will become negative. So therefore what it means is that tau zx is nothing but minus tan alpha 2, and therefore this is negative stress, thereby meaning that this stress will be directed in the opposite direction. So finally what we find is that if we have the surface to be like that, then the stress here will be directed like this, stress here will be directed like this. So therefore this is tau zy stress and this is tau zx stress, and these stresses, it will act along the boundary in the same sense as the applied torque, or applied torque, you remember it was like this, and therefore these shear stresses are really oriented in the same sense as the torques. So all along the boundary you can now draw the direction of the shear stress like this. Now let us try to solve some problems and get to know where the stresses are going to be maximum and how they vary over the whole section. So we will consider some examples. Let us first consider the example of elliptical section. Let us say that the major axis, semi major axis is A, semi minor axis is B, and therefore this curve is nothing but y equal to b by a root over a square minus x square. The equation of the boundary is given by x square by a square y square by b square is equal to 1. So the boundary equation is nothing but, curve is nothing but x square by a square plus y square by b square minus 1 equal to 0. Now we can assume the phi function in this form: m into x square by a square y square by b square minus 1. This ensures that the phi function is 0 all over the boundary. You remember that Prandtl stress function phi has got to be 0 at the boundary. So therefore that is ensured, and we have just brought in one constant m here. Now, to determine this constant, we can write the equation of the equation satisfied by this, or equation that is satisfied by this Prandtl function, that was delta 2 phi delta x square plus delta 2 phi delta y square is equal to minus 2 g theta, where theta is the angle of twist per unit length. Now, if we substitute the value of phi here, it gives us minus 2 g theta, and therefore, this constant m is equal to minus g theta a square b square by a square plus b square. So, let us write that equation number 1. So, therefore, we have got the value of constant m in terms of the angle of twist per unit length and the cross sectional dimensions. Now, we would like to go in for the utilization of another relationship, that the torque applied is related to the phi surface by this relationship, integration of the phi function over the whole area this is nothing but integration. We can now consider that this integration x is varying from minus a to a and y is varying from minus b by a square minus x square to b by a square minus x square, and phi is, we can now write the value of phi. If we write in terms of m into x square by a square, y square by b square minus 1 dx dy. Now, since this section is symmetric, we can make use of some, we can simplify this. This will take the form, it is 4 times 0 to a we can write this also 2 times 0 to b by a square square root a square minus x square m x square by a square plus y square by b square minus 1 dx dy. So, this gives us 8 times m 0 to a 0 to b by a square minus x square by a square plus y square by b square minus 1 dx dy. Now, first we will integrate with respect to y. So, if we do that, zero to a we can take only one term. We will just first just concentrate on this term x square by a square. So, if we consider that this integral, let us say that this is I1 b by a square x square by a square dx dy. So, just I am concentrating only the first term. So, this gives us 8 times m 0 to a, it is 1 by a square, and now this is going to be x square b by a square root a square minus x square dx. So, just integration with respect to y. So, this gives us 8m, it is b by a cube 0 to a x square minus x square dx. Now, if we make this substitution, let us make this substitution x is equal to a cos theta. So, if we make this substitution x is equal to a cos theta, then we have dx is equal to minus a sin theta d theta, and the limits of integration will then become, this is cos theta 0 means pi by 2, and this is going to be 1 means 0. So, therefore, our integral I1 is going to look like this: 8m b by a cube pi by 2 to 0, and this is a square cos square theta, and this is going to be a sin theta, and this quantity is minus a sin theta d theta. That is nothing but 8m b by a cube, and we can now write the limits 0 to pi by 2. So, this minus will be cancelling. So, therefore, this will become 0 to pi by 2. We have now a4. So, a4 can be taken out. We have cos square theta sin square theta d theta, and this means it is, we can write that 2m into ab 0 to pi by 2. We will have 4 cos square theta sin square theta, which can be written as 2 sin theta cos theta whole square d theta, and that is equal to 2 times m a b 0 to pi by 2. This is nothing but sin 2 theta square. So, sin square 2 theta, and that can be written as 1 minus cos 4 theta by 2. So, we can write this thing as 1 minus cos 4 theta by 2 d theta. This gives us 2 times m 2 times m a b, and this is going to give us first term integration is going to be pi by 2 into half is pi by 4 minus it is half 0 to pi by 2 cosine 4 theta d theta. You know that this integral is going to be 0, so therefore this is 0, and we can now write this thing as 2 times m pi a b by 4. Similarly, the integration of the second term, if you consider the second term I2, it is going to be 8m 0 to a 0 to b by a square minus x square, and we will have y square by b square dx dy. So, here also we can proceed in a similar manner, and this is going to give us 2 times m again pi a b by 4. So, the detail you can work out. The third term I3 is nothing but it is 8 m integration of minus 1 dx dy over the region 0 to a, and we can probably write here 0 to a, and this is 0 to b by a square minus x square. In fact, this integration is nothing but the quarter area of the ellipse. So, therefore, we can write now this is 8m, quarter area of the ellipse is nothing but pi a b. So, this gives us 2m pi a b, and this is of course negative. So, finally, if we look into all this, t is equal to I1 plus I2 plus I3. So, we will try to get the value. It is nothing but twice m pi a b by 4 pi a b by 4 minus pi a b. So, this gives us torque is equal to minus 2 m pi a b by 2, which is nothing but minus m pi a b. Already we have obtained the value of m earlier. So, if we substitute the value of m, m was g a square g theta a square b square by a square plus b square with a negative sign. So, therefore, t is equal to minus g theta a square b square by a square plus b square, that is m pi a b. So, this finally gives us it is g theta a cube b cube, we have of course pi here. Let me rewrite g theta pi a cube b cube by a square plus b square. So, this is the relationship between the angle of twist per unit length and the cross sectional dimension with the applied torque. You can see the units are in perfect match. You have G given in Newton per meter square and dimensions will be in meter. So, therefore, we are going to get Newton per meter square into meter square, and therefore, it will give us Newton meter. So, torque will be Newton meter. Now, if I consider the phi function, phi is going to be m x square by a square y square by b square minus 1. Let us substitute the value of m, g theta a square b square divided by a square plus b square into x square by a square plus y square by b square minus 1. Now, if we write this g theta in terms of t, then I can write now here that this is nothing but minus t by pi a b x square plus y square b square minus 1. Let us calculate the stresses now in the cross section. Since we have got the phi, it is possible to calculate now the stresses over the whole cross section. We can now write tau zx, which is given by delta phi delta y. This is nothing but t by pi a b 2y by b square. So, this is t two times t into y by pi a b cube. Again, you can check that the stress, this will become Newton meter square and this is going to be meter 4. So, therefore, we are going to get Newton per meter square, the stress unit. Look at this relationship. The stress tau zx is going to vary linearly with y. So, we can get the value of the maximum shear stress tau zx occurring when value of y is maximum. So, for the cross section that we are trying to talk about, we certainly have the value of y maximum at the extremity of the minor axis, that is y equal to b. So, the maximum stress tau zx, it is going to come up here, it is independent of x. So, therefore, for the cross section, if you look into the cross section, so it depends only on the distance of the point from the x axis. So, therefore, the maximum distance is here. So, it is going to be varying linearly with y, and it will have maximum value at this point, and this is now at x is equal to 0, y equal to b, and the value is given by minus 2 times t into b by pi a b cube, and that is 2 times t by pi a b square, and this stress is negative. Now, remember that we have been considering the torque to be applied in the anti-clockwise direction. So, therefore, the torque is acting like this. The positive stress will be acting in this direction. So, that is your positive stress, but this relationship shows that the maximum stress is going to be negative. So, therefore, actual direction of the stress is going to be in the opposite direction. So, therefore, this is really the direction of the stress tau zx. So, therefore, this is not the direction. So, this direction is not really correct, and it is in conformity with the torque direction, that it should be in the direction towards negative x. So, that is the point you must note. What we have got here, that the shear stress is varying linearly along the y axis. So, therefore, it is varying linearly along the y axis like this. For a particular x, the variation is linear and it is maximum at that point. Now, let us see what happens to the other component of stress, tau zy. Tau zy is nothing but minus delta phi delta x. So, if we now write, it is going to be t by pi a b, and this differentiation is going to be 2 x by a square. So, we will have 2 t x by pi a cube into b. So, it says that tau zy stress is proportional to x, it does not depend on y location at all. So, therefore, we will have the maximum value of x coming up at the end of the major axis. So, therefore, the stress is going to vary. If you consider the x axis, it is going to vary from origin to this point linearly, and it will have maximum value, and you see that the direction of this stress is going to be positive, means this direction, and it is really so. So, and it is again in conformity with the applied torque direction. So, the variation of the stress, let us draw it here. So, this is your tau zy and this is tau zx variation. Now, tau zy maximum is occurring at x is equal to a, y equal to 0, and if we write that, it comes out to be twice t by pi a square b. So, we have seen the distribution of the stresses over the cross section. In this case, the stress is varying linearly over the minor axis, so also over the major axis. If you would like to show the stresses in the same sense as the torque, then this will be the direction. So, you can show them to be tau zy rather than this. Now, the magnitude of the maximum stress here is given by 2t by pi ab square, and the magnitude of the maximum stress here is given by 2t by pi a square b. Look at this, the value of the stress at this point is higher. So, therefore, the section would have the highest stress at the end of the minor axis. So, wherever the distance is lower, there you get the maximum stress. So, therefore, the tau zx maximum is higher than tau zy maximum. So, in this cross section you can certainly show the stresses to be like this, as we have shown in the case of circular cross section. It is going to be like this here, and it is going to be varying like this. So, the stresses are this is how the stress pattern will be given, provided the torque is acting like this. Now, let us consider another cross section which is triangular. It is equilateral triangle, and the dimension is given by A here. The torque is acting in the anti-clockwise direction like this. Let us find out where is the maximum stress. In this case, we expect as usual the stresses to be acting parallel to the boundary. So, we can show the direction of the stresses to be there like that. The equation of the line OA is nothing but y tan 30 x. So, therefore, 1 by root 3 x. Equation of OB is y equal to minus 1 by root 3 x, and AB is x is equal to A. Making use of the equations of the boundary, we can write a phi function like this: y square minus x square by 3 into x minus A. This is the equation. Now, if we relate the torque to the phi function, we have phi dA over the whole area, and therefore, this is 2m integration of the quantity zero to A, and we can have now y root 3 y equal to x by root 3 x minus A y square x square by 3 dx dy. So, if we integrate with respect to y first, x minus A 0 to, we can now, this is symmetric, so therefore we can really write this thing as 0 to x by root 3 and integration of y square x square by 3 dy dx. To m 0 to a 2x minus a, this is going to give us y square, I am sorry, this is going to be x cube by 3 root 3 minus x cube by 3 into root 3 dx. So, this gives us 4 0 to a x minus a into minus 2x cube by 9 into root 3. Yes, I think we have some error introduced here. The equation of the line AB should be, it should be root 3 by 2a. So, therefore, this quantity will come here, root 3 by 2 at all, root 3 by 2, here also root 3 by 2, root 3 by 2. So, this gives us minus 8 by 9 into root 3, 0 to a x minus root 3 by 2a into x cube dx. Of course, variable of integration is there. Once you do all this, now the integration is straightforward. So, I would not like to carry on doing it for you. So, this will give us finally, it is m a to the power 5 divided by 80. So, further integration will give you this quantity. Therefore, t is equal to m a5 80 and hence m is equal to 80 t by a raised to the power 5. Let us now get back to the expression for the phi function. Phi was given as m into y square minus x square by 3 x minus root 3 by 2 into a. Now, if we substitute the value here 80 t by a5 x minus root 3 by 2 a. Let us calculate the stress tau yz, which is given by delta phi minus delta phi delta x. So, this will give us minus 80 t by a5 minus 2x by 3 x minus root 3 by 2 a plus y square x square by 3 into 1. So, that is the variation, and you can see that the stress varies quadratically for a particular value of y. So, tau yz varies quadratically for y constant. Typically, if you like to consider tau yz for y equal to 0 and x is equal to root 3 by 2. So, let us get back to our extreme point. So, extreme point is x is equal to root 3 by 2 a. So, if we substitute that, then it comes out to be minus 80 t by a5. Here this is going to cancel out and we are going to have minus it is 3 into root 3 by 3 I am sorry, it is going to be 3 by 3 4 a square. So, this gives us 80 t by 4 a cube, which is nothing but 20 t by a cube. So, the stress which is going to be occurring at the end point of the x axis. So, if you consider this point, at this point the stress is going to be 20 t by a cube. So, we have got the maximum stress. If you would like to consider again a point like this, you will find that these are all going to have same stresses. The stress position here and here, they are identical, and you will find that the stress is going to have magnitude of this value 20 t by a cube. Now, let us try to consider what happens to the corner. So, we have this section like this. If we consider that the stress here at this boundary is directed like this, for the applied torque this way, then the stress along this boundary is going to be directed like this. Now, at this point it is a common point. So, the stress at this point is going to have duality in terms of direction. So, therefore, there cannot be duality of stresses at a corner point, and therefore, the stress at this corner is going to be 0. So, this cannot be a point with stress. So, shear stresses are 0 at this corner. Same logic will apply to this corner and this corner. So, whenever you have any corner occurring in the cross section, you will find that the stress is 0. We will consider cross section which is little easier to understand. We will consider now a section like this, rectangular cross section. So, I would like you to think about it, and we will continue with this example in our next presentation. Let us select the coordinates like this. This height of this section is 2b and the width is 2a. What should be the form of the Prandtl stress function here? Please try to guess. You have the two boundary which are vertical, which are located at x is equal to minus a and plus a, and you have two horizontal boundaries which are located at y equal to minus b and plus b. So, therefore, in this case, without any difficulty, we can make an approximation about the phi function in this form: m into x square minus a square y square minus b square. So, this is the phi function. Now, in this case, what do you expect to be the stresses? Just guess that you have to have a phi surface, and looking into the analysis of elliptical section, try to guess what is going to be the stress variation, and at the same time what do we expect the maximum stresses to occur. The stress directions are going to be parallel to the boundary like this. This is the direction of torque, and the stress here is nothing but tau zy, and the stress at the end of the y axis is tau zx. So, we will like to find out these stresses in the next class. It will be good idea for you to just find out the stresses starting with this Prandtl stress function.